A successful strike from an anti-tank weapon is a physics problem. It initiates a sequence of predictable mechanical and physiological events. The primary event is armor penetration. The aftermath is a subject of forensic analysis. What happens to the crew's physiology in the milliseconds after this event? The interior environment transforms. A pressure wave expands through the fighting compartment. Metal fragments, or spall, are ejected from the inner armor wall at hypersonic speeds. The temperature spikes. The probability of crew survival is not a matter of chance. It is a function of the vehicle's internal architecture and the placement of its ammunition. This is a core engineering calculation. Data from destroyed platforms collected by recovery teams confirms this relationship. The T-90 platform serves as a case study. The final state of the vehicle and its crew is a direct consequence of its initial design architecture. The internal architecture of Soviet tanks was not simply an engineering matter. By the 1980s, it became a symptom of a systemic logistical crisis. The state required a unified platform. Two paths were proposed. The first was Object 188, a deep modernization of the existing T-72. The second was Object 187, a completely new design with a radical hull and turret architecture. Prototypes for the new designs arrived in 1990. But in 1991, the Soviet Union collapsed. The state had envisioned a revolutionary armored vehicle. The reality was a choice dictated by economic ruin. In the underheated halls of post-Soviet factories, the echo of footsteps replaced the sound of production. The new Russian Federation inherited a fractured industrial base. Of the 5 primary Soviet tank plants, only 2 remained on its territory: Uralvagon Zavod and Omsk Transmash. Launching a fundamentally new platform was no longer feasible. The choice was made for them, not by engineers, but by the state's collapse. The government selected the safer, more cost-effective option, the heavily upgraded T-72, then designated T-72BM. It was not a technological leap, it was a compromise. To signify a clean break from the past, the Ministry of Defense officially redesignated the T-72BM as the T-90. The T-90 was meant to resolve a crisis of standardization, a crisis with roots extending back to the 1960s. It began with the introduction of a single platform, the T-64. For its time, the T-64 was a revolutionary design. It featured a 125mm smoothbore gun, an automatic loader, and advanced composite armor. But its complexity made it expensive to produce and difficult to maintain. The tank was reserved for elite Soviet Guards divisions. A parallel solution was required for mass mobilization. That solution was the T-72, a simplified, cheaper tank built for conscript armies. Why did the state require 2 independent production cycles for a single tactical role? The answer was doctrine. One line for elite units, another for mass deployment. Then, a third line appeared, the T-80. The T-80 was an attempt to refine the T-64 concept. It introduced a gas turbine engine. The high-frequency whine of the turbine became its signature sound. It granted superior speed and acceleration, but at a severe logistical cost. The engine consumed 2 to 3 times more fuel than a standard diesel. This rendered it unsustainable for large-scale operations. The T-80, like the T-64, was issued only to high-priority formations. The result was systemic inefficiency. 3 factories produced 3 different main battle tanks. In Kharkiv, complex components for the T-64. In Nizhny Tagil, simplified assemblies for the T-72. In Leningrad, power-hungry turbines for the T-80. All performing the same function, none sharing critical parts. By the mid-1980s, the Soviet military was forced to support 3 separate logistical chains, 3 distinct crew training programs, and thousands of non-interchangeable components for its frontline tank forces. The state sought a unified solution, one based on a proven, mass-produced chassis. The foundation was the T-72. This new vehicle inherited its core architecture, a low profile, an autoloader, and a 3-man crew. The first layer of defense was reactive. Blocks of Contact 5 explosive reactive armor were integrated across the hull and turret, designed to defeat shaped charge and kinetic energy penetrators. The second layer was electronic. An infrared jammer system, designated Stora-1, was added to counter anti-tank guided missiles. Two prominent infrared projectors flanked the main gun. On activation, they emitted a pulsating red light, distinctive glowing eyes. Laser warning receivers and smoke grenade launchers completed the active protection suite. But could new electronics compensate for an old architectural flaw? Designers were aware of the vulnerabilities. They attempted to improve protection for the ammunition, yet the core problem was inherited directly from the T-72's layout. A carousel of high-explosive shells and propellants remained stored openly within the fighting compartment. The systemic vulnerability of this ammunition layout was about to be proven. The city was Grozny, the year 1994. During the First Chechen War, Russian command ordered columns of T-72s and T-80s into the urban center. They advanced without sufficient infantry support, a critical doctrinal failure. In the tight streets, ambush teams waited. They were positioned across multiple floors of ruined buildings, armed with rocket-propelled grenades. The tanks were channeled into kill zones. Attacks came from all directions, but especially from above. There was the sharp hiss of a cumulative jet, a stream of molten metal slicing through the vehicle's thin roof armor. This plasma jet instantly ignited the propellant charges in the autoloader carousel, a design flaw demonstrated on a catastrophic scale. For decades, this same roof vulnerability would remain, a weakness waiting for new technologies to exploit it. The entire ammunition load detonated. The turret was thrown clear from the hull. 30 years later, the threat from above evolved. On the battlefields of Ukraine, drone operators replaced grenadiers. The West's most advanced platforms arrived: Abrams, Leopards. They were intended to be a decisive factor. Instead, their crews revived techniques from 1944. Crude metal cages were welded to turrets. Sandbags were piled on engine decks. High technology met improvised defense. Are tanks obsolete in modern warfare? The race between armor and shell has reached a technological dead end. The answer is in the physics of the fight. The logic of protection was an escalating cycle. Explosive reactive armor countered shaped charges. In response, designers developed tandem warheads. The first charge detonates the reactive block. The second penetrates the hull. Armor was improved again. Then the paradigm shifted. The threat was no longer just horizontal. It was vertical. Small, inexpensive drones appeared over the battlefield. The first response was physical. Steel grates, nicknamed cope cages, were mounted to provide distance. They were designed to detonate a warhead before it reached the main armor. But the next evolution was already in development. A $500 FPV drone against a $3 million tank. The economic equation of war was broken. The countermeasure to the cages was precision. Jamming devices were ineffective against fiber optic drones. An operator could guide the munition in real time, steering it past defenses, identifying the weakest points. The thin top armor, the engine vents, the gap between turret and hull. Armor was technologically powerless. The search for a viable solution to armor's deficiencies was now a state-level priority. In 1999, the Russian command redirected its newest assets, T-90 tanks, originally built for export, were rerouted to the escalating conflict in Dagestan for combat trials. This was a significant deployment. National economic crisis had slowed production to a near halt. By 1998, only about 150 units were in service. Each machine was valued at millions in potential export revenue, making any combat loss critical to the military-industrial complex's budget and reputation. The propaganda narrative required a battlefield success. Later, in 2015, the platform saw action in Syria. A widely distributed video showed a T-90 surviving a direct turret impact from a TOW missile, its Contact 5 armor seemingly deflecting the warhead. However, independent analysis documented a tactical flaw. Insurgents had developed a method to defeat the reactive armor. Multiple RPG teams would concentrate fire on a single area of the tank. This sequential targeting stripped the contact 5 blocks, exposing the vulnerable primary armor. The tank was not invincible. It could be systematically dismantled. Official reports from Dagestan emphasized the tank's resilience. They cited one specific case of a machine continuing to operate after taking 7 direct RPG hits. The Syrian campaign produced contradictory data. While individual tanks demonstrated resilience, systemic vulnerabilities and economic factors forced a strategic reassessment. The T-90 platform was upgraded, receiving a 1,000 horsepower diesel engine. It was more fuel efficient, but it retained a notoriously slow reverse speed, under 3 miles per hour. The heavy drone of the engine in reverse became a known audio signature. The main armament remained a 125mm smoothbore gun, compatible with existing ammunition and guided missiles. This raises a central question. Why did a modernized 1990s platform become the foundation for 21st century armored forces? Because alternative projects had failed. New generation tank programs never advanced beyond blueprints and prototypes. The economic calculus was clear. The cost of one new T-90 was equivalent to the deep modernization of 3 older T-72 tanks. This was a critical factor. In 2012, the decision was made. Production lines for the base T-90 model were halted. For nearly a decade, the program was frozen. By 2020, with no viable replacement, the military-industrial complex presented a revised solution: the T-90 Model 2020. It featured improved fire control systems and new digital displays for the crew. It was a product of necessity, not innovation. The updated model received improved armor and, in some configurations, a cage for overhead protection. The gun stabilization systems were enhanced. It was formally adopted into service. Just before the start of a new large-scale conflict. The primary instrument for neutralizing modern armor is kinetic energy, a long rod of dense metal, an armor-piercing fin-stabilized discarding sabot, or APFSDS. Its method of destruction is raw velocity. The penetrator, typically made of tungsten or depleted uranium, travels at speeds exceeding 1,500 meters per second. This is more than twice the velocity of a standard Army-caliber bullet. What happens when such a rod strikes armor? The impact energy instantly vaporizes the metal. The point of contact generates a dazzling flash. A cone of superheated molten fragments is projected into the turret's interior. A lethal spray. The physics are absolute. There is no explosive filler. None is needed. The material of the penetrator dictates its behavior. Depleted uranium exhibits a unique property. It self-sharpens through adiabatic shearing as it passes through the target, maintaining a cutting front. This process also creates a cloud of fine pyrophoric dust, which can ignite spontaneously in the air. The internal space becomes an overpressure event, equivalent to a detonation. The dense rod continued its path, shredding internal systems and ammunition racks. However, armor penetration is not a prerequisite for destruction. A main battle tank can be disabled without a single breach of its hull. A documented case involved a Russian T-90 engaged by a Ukrainian Bradley fighting vehicle. The Bradley's weapon, a 25mm chain gun. Its intended target was not the tank's composite armor, but its external systems. The Bushmaster cannon delivers a rate of fire up to 200 rounds per minute. This density of fire makes the destruction of exposed optics and sensors a statistical probability. The T-90's fire control was systematically blinded. Its turret began to spin without command. The driver lost control. The tank crashed and was immobilized. The crew abandoned the machine. According to reports, 2 crew members were later killed. A main battle tank, with its 125mm gun, was rendered inert by a far lighter platform. The immobilized machine was later destroyed by ordnance dropped from a drone. With the tank inert, its fundamental vulnerability is exposed, a flaw not in the armor, but in its core architecture. The foundation of Soviet tank design, the autoloader. This system, inherited from the T-92, is a rotating carousel positioned directly beneath the turret floor, under the crew's feet. It holds 22 rounds for the main gun. The ammunition is stored in two pieces, a projectile and a separate propellant charge. Why is a catastrophic detonation almost inevitable upon penetration? The propellant charges are far more volatile than the projectiles themselves. When a fragment pierces the armor, it ignites a casing. A sudden, massive spike in overpressure fills the sealed interior. This heat triggers a chain reaction, consuming every charge in the carousel. The result is a violent internal explosion. The force has one escape path, upwards. It ejects the 12-ton turret from its ring. This event renders the hull structurally compromised, unrepairable. The asset becomes a total loss, unable to be recovered or rebuilt by the state's industrial base. This guaranteed self-destruction is a direct consequence of prioritizing a low silhouette over crew and vehicle survivability. In early models, approximately 20 additional rounds were stored inside the crew compartment wherever space permitted. To address the known vulnerabilities of ammunition storage, later T-90 modernizations introduced partial engineering solutions. The design incorporated a new bustle at the rear of the turret. This section stored 8 to 10 additional rounds. It was equipped with blow-off panels, a concept intended to direct an explosion upwards, away from the crew compartment. This change mimicked Western safety standards. A superficial change. The fundamental architectural flaw remained untouched. The primary autoloader carousel, with 22 rounds, still occupied the whole floor directly beneath the crew. To mitigate this, engineers added internal spall liners and reinforced armor around the carousel mechanism. These additions proved insufficient against a direct penetration. Even the automated fire suppression systems offered only a marginal benefit, providing the crew with mere seconds to attempt an evacuation. This reality forced a tactical adaptation from the operators themselves. In response, experienced crews began entering combat with a deliberately limited load, refusing to carry any ammunition beyond the 22 rounds in the primary carousel. But avoiding ammunition detonation does not guarantee survival. A kinetic strike on the T-90's hull initiates a different, more insidious chain of lethal events. What happens when the armor is not penetrated? The shockwave transfers immense energy through the steel. This energy detaches fragments from the interior armor wall, a phenomenon known as spalling. The crew compartment is instantly filled with a high-velocity cloud of razor-sharp steel. A barometric pressure wave follows. It ruptures eardrums. It damages lungs. The human body is crushed without a single external breach. Every impact also ignites a chemical threat. Burning plastics, insulation, and technical fluids create a dense, suffocating smoke, a toxic fog. In cases involving depleted uranium penetrators, another layer of hazard is introduced. Microscopic radioactive dust invisibly contaminates the crew space, settling in the lungs and on mucous membranes. A crew might exit the vehicle seemingly unharmed, yet their long-term viability is compromised. The training of a qualified tank crew requires months of investment. The loss of such personnel to secondary factors represents a severe strategic depletion of human capital. This leads to the ultimate fear for any tank crew: fire. An internal explosion is final, instant. But fire is a slow, conscious process, a reality understood second by second. While the T-90 platform continues to see upgrades in armor, optics, and engines, these internal vulnerabilities are not addressed. The vehicle is still in operational use today. The fundamental architecture is unchanged.